Alright, hello everyone. Sorry I've been away for a little while. I was concentrating on a video regarding relative density, gravity, all those kinds of things, and I just decided to put that on the back burner for now, um, and return a little bit to some optical observations. So I think you'll find this one interesting. So I decided to make this one sort of my proof for bottom first disappearance across flat surfaces or relatively flat surfaces, undisturbed by irregularity or obstruction. And I'm calling this Appendix A essentially for Concept for Vision, which you can find on my channel for a more in-depth explanation. So my intent for this is to be short and to the point. So this is across a lake nearby, which on a perfectly clear day, decent weather, and it's about 410 feet across to the other side, where there'll be a piece of debris that you will see here in a minute. So I'll go ahead and play. So I'm lowering my iPhone from about a 2-foot height down to just where the water ripples, and that's just when the casing on the iPhone just barely touches the water. Right there. So the camera is inverted. It ends up being about a ½ inch above the water. This is zoomed in. You can see the white piece of debris by the bench to the lower left of the bench, across the way. So you'll see there it's gone, and I haven't even touched the water yet. There, I've touched the water and it's back again. So I decided to put some measurements to this, which we'll discuss in a minute. I also want you to note that piece of white debris right there in the center of the frame that is very nearby, around 15 feet away, and how close that gets to the horizon as we lower our phone down. So these are some still shots from what I just showed. So again, distance is 410 feet, and that near field debris is the red arrow in the left picture there in the low aspect of the frame. And then as I at about a 2-foot observer height, and then at about a 0.5 inch observer height, you can see how high in the field that piece of debris got near the purple mirror inflection point or horizon line of this image. So again, keep in mind that if this is, let's say it's 10 to 15 feet away, and the distance between myself and the debris on the other side is 410 feet, that I am cramming 400 feet of information between the red tip of that arrow and the purple horizon line, which is a lot of information. And so what ends up happening is that your horizon shortens along the lower field, and whatever is there disappears into the essentially a gap that's formed. So to illustrate this a little bit more, you can find this explanation on the lecture version I guess I did with Jeranism on his channel about angular resolution and so forth, but I just wanted to reiterate it here because I think it's important. So again, this is just a typical photo with a iPhone camera about 6 feet off the water, and I am basically looking at a cresting wave, which you can see in the zoomed out photo. You don't even need to be zoomed in. You can see the little white dot that the arrow is pointing to in the middle of the frame, and then zoomed in you can see it a little bit better. But how far is that cresting wave, do you think? So when you analyze this, you find that it's essentially about a ½ mile away. You can find a more in-depth discussion on how these numbers all work out and why it's only about a ½ mile away on, again, that a concept for vision, or the discussion with Jeranism. But each halving of a frame puts twice the amount of information in the next halving. So you can look at the 50% numbers on the side. You can look at the amount of information that I'm cramming into each subsection. And again, the proof of this you can find when I analyze the hallway footage and you find that in, again, the lower 1/4 of the image I have 9 feet, and then it goes 18 feet, 36 feet, 72 feet, and it doubles each time. And by the time you get to the arrow point, it's only about a half mile, which means that if I'm a 6-foot observer and I see 3 miles, then I'm cramming 2.5 miles between the very top black line and the purple line horizon, which is quite a lot of information to be crammed in such a small space. So I'm not going to go through this in too much detail. I want this to be short. Just remember that as you lower your eye height, you're cramming more and more information into a smaller space, and it gets lost. So, but it remains 50% of your vision. So the floor is still 50%, even though you're not seeing as far along the floor. So what happens to that information in the distance? It disappears essentially into this what I'll term, I guess, a horizon. Same thing here. Again, at different heights, you can see how I'm compressing different information. So when I'm 8 foot tall, the ceiling is getting compressed, and as I get down to 1 foot tall, or 0 feet, or essentially half a centimeter off, the floor is getting compressed. And this is just an aspect of how our vision works. It has nothing to do with curvature. So these spacings, again, just to reiterate, they are spacings along regular intervals that were measured, and you can see how that information changes as I alter my height to them. More and more information gets compressed into smaller spaces. And this is just taking them away from the photos to analyze them. And then putting kind of a side-on view, which again doesn't really exist, but just allows you to kind of conceptualize things a little bit easier. And some more math on how the floor tiles worked, the spacing along the lights, and how all the mathematics works out essentially to give us this halving phenomenon between each iteration of a frame. And this is at different heights, and again, how you see different aspects within each halving of an image, and how this phenomenon might allow for bottom first disappearance as the horizon along the lower field shortens, and we do not see as far along it. And what ends up happening is we form this gap of sorts in our vision. If we are close to the ceiling, let's say, and it were flat, we would have a gap along the ceiling, and we wouldn't see as far along the ceiling, but we would see as further along the floor. And the vice versa occurs when we are closer to the floor than we are to the ceiling. And my point with this is that we are always, when we are outdoors, closer to the floor than we are to the ceiling. So as I lower myself in this perspective here, and I have a light visible across about 400 feet or so, or 500 feet of distance along a hallway, you can see that the light is visible at first, and then as I lower myself, how perspective changes. So if we change our, if we go from a hallway into an outdoor setting and we just change our horizon distance, there's no reason why this isn't a different aspect of perspective. It's the same exact thing. We're just outdoors. And instead of looking at a flashlight, we are now looking at a cruise ship or a boat or something else going over what we believe is a physical horizon, but is nothing more than an apparent position of our vision and how our vision works along flat surfaces. So same thing again, I'm in here in a Walmart, and then no light is visible. I'm along the floor, so there's no reason to believe why this aspect of vision would change if I were to remove the walls and the ceiling of this Walmart and extend this floor for miles and miles, and I were just to stand up. It would be the same exact phenomenon, but just occur further and further away. There's no reason to believe that this is curvature. So I just do that here. I remove the walls and the ceiling. I'm still on the floor. and then I extend my floor, let's say, to become some crops or something like that. It doesn't matter. And now I'm just looking at a tractor going off into the distance, and it disappears as well. So here's the footage with some more exact measurements, and this is just later in the day. And so you can see kind of what occurs along this flat surface. And I'm calling it flat because by globe standards, this is a flat surface. Essentially no bulge is apparent across 400 feet. But yet we have an issue here. So please watch.
Okay, here we are at the lake. It's a nice clear night. Perfectly still waters. I'll put the coordinates on Google for where exactly I am across this lake, and the distance of the light height, the distance of the light height, and the iPhone height. Bye.
So here we are, we're taking it at 2.5 inches just to be in the middle of the light. Here's the setup. And there I'm just barely touching the ground, touching the water. You can see the ripples just starting as the iPhone case just touches the water. There's no immersion of the camera or anything under the water. Here it is zoomed in a still shot. Missing now. Slow motion. You can see the autofocusing occurring, and I stopped it here so you can see kind of that there appears to be basically a hard line on this frame. And again, just some more slow motion of the other times that I went up and down. So these were the distances. So again, 0.1 to 0.2. I basically sat there for about 2 or 3 minutes and allowed the positioning system to identify where I was before I pinpointed each point, and that's very accurate for at least where I was. So could it be a few feet off one way or another? Sure, but roughly it's about 400 feet at least. Again, you can see the measurement of my iPhone case to the center of the camera, and it is about half an inch. And you can see that I took the 2.5 inches for the height of the light, which was being generous. I didn't do the top of the light, which the whole light disappears, but I'm just going to do the middle of the light. And so some still shots again. As I'm about 1.5 feet off the water, you can still clearly see the light, and you can see a little bit of reflection on the water with the light, but the light is still visible. And then as I am 0.5 inches off, there is clearly no light visible whatsoever. And then in the bottom of I just took some still shots of how that when it was autofocusing, and you can see the halo, and how that halo definitely appears to be cut off bottom first. So what should we be seeing if we were to be living on a globe? If this phenomenon right here is because this water is curved, and curved water is what obstructs our vision of things beyond a horizon, a physical horizon, then what should we be seeing? Well, the short answer is that we should be seeing this entire light. There should be no loss. And so the drop essentially should be about 0.004 feet, or about 0.048 inches, or which comes out to about 1.22 millimeters. And if you know how big a millimeter is, that's extremely small. And we are definitely far more than 1.22 millimeters with that light above the water. Furthermore, my horizon distance should be about 1,314 feet, which is well beyond the 400 feet that we were at. So by all accounts, we should be seeing this entire light the whole time. So if we go to some Earth curve calculators, you can see again by their mock-ups that there should be nothing hidden in this situation. It should be completely visible with a globe with an R radius of 3959 miles. Or something else occurs in our vision to cause this effect. Once again, just confirmation that the bulge height is extremely small in this situation and that the hidden height is nothing. So in this situation, this curve calculator says 0.3 millimeters is the bulge height, which is negligible. And again, yet we have 2.5 inches are being obstructed in this situation. So another curve calculator. And again, notice that all of them model this as if you are looking down across a bulge, and that's why things disappear, is because you're either leaning backwards and looking across a bulge in front of you, or your eyes are tilted down and the object is tilting away from you. That's how this is modeled. This is not how this works. So again, under no situation should we see this kind of obstruction. Some more Earth curve calculators, again, 0 millimeters, 0 feet, 0.00 feet. One of them gave 0.237 inches, so one of them gave at least a 0.23 quarter of an inch, but that doesn't matter. Again, we were 2.5 inches off the water, and so there was no refraction. You could not really say that this wasn't a refraction phenomenon if you were to go back and look here at these conditions. This is across 400 feet. It's crystal clear. The water is not moving whatsoever, and the temperature is roughly the same between the water and the outside air. It was a fairly warm night, so
Okay.
I'm not too concerned that refraction would play almost any role in this whatsoever. So being generous and negating the loss of our 0.5 inch observer height and granting 2.5 inches of drop basically as the midpoint of the flashlight, not the top even, what should the radius of Earth be if we're going to assume that bottom-up obstruction is always caused by curvature? So in other words, if I'm losing 2.5 inches across 400 feet, what kind of radius would that purport to, right? What kind of globe should I be standing on if bottom-up disappearance is caused by physical obstruction? So when you do the math for this using trigonometry, where our theta angle comes out to 0.0175 degrees, which is again close to 1 arc minute, and our height of about of 2.5 inches of drop, then you end up with 870 miles of R. So R is 870 miles in this case, which is well below the 3,959 miles that is purported to be. You can use an alternative method using the 8-inch drop approximation for the first mile versus our 2.5 inch drop over our 410 feet. You can just analyze the ratios between the two and you get to something about 4 times greater curve rate because our obstruction is just too much. And so, or it's about 1/4 the R basically. So as approximation again, but you get something where 990 miles. So we can just you can average some of these methods together, and you can say that roughly we should be standing on a globe that's about a radius of 900 miles. And we're just going to use it as an approximation. So our new Earth circumference is 5,654 miles versus the expected 24,800 miles that they say it is. So Earth is now 1/4 the size it should be, and it ends up being smaller than the Moon, using the rationale that this is a physical curvature phenomenon. So you can believe that, or you can believe something else is responsible for this bottom up first, or this bottom first disappearance phenomenon. So is information loss an everyday aspect of our visual horizons? Is it why is this occurring? Is it secondary to tangible surfaces? In other words, to our proximity to a tangible surface limits the amount of information that we're being allowed to process. So I just want you to focus on that. It may not be that the bottom of the objects disappear from being too small to see, but rather that the ground can only extend so far when we are close to it. We can only see so far along the ground. It's not so much the object itself or the bottom of the boat itself getting too small. It's the fact that you can't see that far along the ground, but it still occupies 50% of your vision. So why do we see in perspective? Is it a property of distant light propagation toward the observer near tangible surfaces? Is it the observer's ability to discern horizon distance based on that incoming information? The diffraction limit of the ground being met prior to the object itself? Some combination of the above? None of the above? I don't know. It does seem that there's an absolute to our horizon. And it seems consistent with around an arc minute of distance secondary to observer height all the way to around 25 miles. If you want more information on that, you can look at all the videos on my channel where we go into that into a little bit more detail. But there's multiple other reasons as well that what it could be. But it does not seem to be a physical curvature phenomenon. That it does not seem to be. So, you may ask, why do we see in perspective in the first place? Why do we even see this way? That's something that I've been trying to ask as well. Why do we see the world the way we do? Is it the diffraction limit of the ground met and the object has no other option from there but to sink into the observer's horizon gap, kind of similar to what I described, as a discrepancy between the upper and lower visual fields? Is it something else? And I've been taking, we're doing a lot of reading, especially with Steinmetz. And can you extrapolate a little bit with what he's saying? Not about vision or anything else, but what he has to say about dielectric and magnetic fields. And I just found one of his pictures of the electric field of a conductor very interesting to me, and how closely it matched to the transversal and orthogonal lines that we see in perspective. And so it's complete conjecture, I'll totally admit. I just found it very interesting, so you can take from it what you will. So again, are we looking down the barrel of a conductor possibly? Is it the phenomenon of a property of light itself as the information propagates towards us, and it's we can only see so far because it's kind of like a damping signal. Damping signal is, or the signal is getting damped so that you can't pick up on as much information. I don't know. And so all these again are we potentially on more of a Mercator projection than an AE one? This kind of simulation theory, it's hard to tell. I don't know the answers to any of these things. I don't know that anyone knows. So I'll leave it kind of to that. So is this going to remain a mystery, an unsolved mystery while we're here on Earth? And I would say that it may be, and that's okay with me. I would hope that everyone analyzes kind of where they're at in this world and sees it for the beauty it is, the unsolved mystery it is, and know that maybe there are things in this world that we're not supposed to know. And I think I'm perfectly okay with that, and I think it's exciting. And so I am happy to know that I am a created being. I pray that you are happy with that as well, and that we all take advantage of everything while we're here to the utmost, especially knowing and being granted this great revelation, in my opinion, of what this world may and may not be. I think it's outstanding. So I will leave it there, and God bless you all.